Hello, today we are covering tangents and circles. So you guys will be able to use the property of tangents and you guys will be able to solve problems involving circumscribed polygons. Now we have learned about tangents before when we were talking about sine, cosine, and tangent, but this is slightly different when we're using it with circles. So our new vocab here is a tangent, point of tangency, and common tangents. So we have a tangent is a line in the same plane as a circle that intersects the circle in exactly one point. So over here you have this example where the line actually is only intersecting the circle at one point. I know sometimes on our pictures it looks like it's touching in more than one point, but it only touches in one point and the other ones are just really close to it. And that point is called the point of tangency. So we have line AB is tangent to circle C at point A. You could also say segment AB is tangent and ray AB is tangent as well. So a common tangent is a line, ray, or segment that is tangent to two circles in the same plane. In the figures below, we have that happening. So L is tangent, line L is both tangent to circle F and G, and on this example as well. So we're going to do some examples. We're going to draw some common tangents. If no common tangent exists, state that. So this first one, we are going to draw a line. Remember, a tangent can only touch the circle in one spot. So is there any possible way to make this line tangent to one or both circles and only touching at one spot? There is not. Now in class we talked about how maybe what if we had a ray that touched the circle and went through the other side? Could that be considered a tangent? Now we'll get to why that's not actually able to be a tangent in a little bit, but for now we can just know that we have no common tangents. Okay? On this one over here, we saw previously that we had a line going through them like this. The thing is, this guy is slightly different than our example above, where we are actually touching both circles in two spots. So what if we rotate it and just have it along the outside? It's one way to do it. You could also put it down here like that. That'd be another example of a tangent line or common tangent line. We'll do it down here. These are actually the same as our example above. We can have it how they did through here. You could also have it through here, basically the same thing. Another way is along the top. And another way is along the bottom. These are all ways that you can draw tangent lines or common tangents, but I'm only going to do that one example. And this one also has a bunch of examples. Once again, you can go through the middle, assuming that these are actually tangent circles and not when you zoom in slightly overcrossed. We're assuming that they're actually tangent. And then you could go on top as well as on bottom. So those are all valid ways to draw tangent lines. So we have theorem 1010. In a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So this is why we could not have this being a tangent ray. Because you have to be able to, from the center to the point, make a 90 degree. Maybe that's not even the best example here. Let's try this. We still have to be able to make from the center to the line a 90 degree angle. And that definitely is not 90 degrees, so we can't even use that as an option. That's why no common tangent exists. Anyway, back to the theorem. This basically states line L is tangent to circle S if and only if these are perpendicular. So we know this is tangent if these are perpendicular. Or if we're told this is tangent, we know these are perpendicular or crossing each other at 90. Okay? So, we're going to use that. KL is a radius to circle K. Determine whether LM is tangent to circle K. So we're deciding, is this a tangent line? Now we are told we have a radius. It comes down and meets the tangent at the point of tangency. So what we are really going to check is if this is a 90-degree angle. And we can do that by using Pythagorean theorem. We take 20 squared plus 21 squared. That should, if it is a tangent line, equal 29 squared. So I already did all the math over here. So 20 squared is 400. 21 squared, we need to back that up so I can see it, is 441. And 29 squared is 841. So you check to make sure this works out. And it checks out. So we know that LM is tangent to our circle K. And then we need to justify our answer, so that would be because KL is perpendicular to ML. And we checked with Pythagorean theorem. And we can also say, like, that was theorem 1010 that we used. We have another example of this. XY is a radius here. Determine whether YZ is tangent. Once again, we're just going to check to see if this forms a 90. So we take 14 squared plus 16 squared. Notice this has to be the hypotenuse. So that equals 21 squared. We have 196 plus 441 equals, or should equal, let's see, where's that? Oh, I'm so sorry. This is 441. This is 256, I believe. There we go. That's better. So 452 does not equal 441. So this is not a right triangle. Thus, YZ, segment YZ, is not tangent to circle X because X, Y, and YZ are not perpendicular. Okay? Now, we move into solving for X. We're assuming that this is tangent, which means this must be a 90 degree. Okay? So to find the value of X, we're just going to use Pythagorean theorem. Now, sometimes it's just simple Pythagorean theorem. They'll give you the whole hypotenuse, yada, yada. This one's a little different. I do want to point out, though, that you know all radii are the same, so these are both X's. That's totally fine. Either way, the first part is pretty simple. You know X and 24 are both legs, so that's X squared plus 24 squared. That must equal the whole hypotenuse, so that is X plus 16 all squared. Now we have to recall some stuff from Algebra 1, mainly foiling to be able to solve. Now foiling stands for first, outside, inside, and last. And you just multiply these, so X times X is X squared. 16 times X is 16X. X times 16 is also 16X. And 16 times 16 is 256. You can bring down the rest of this. What is 24 squared? 576. And then you can combine like terms on the right side. Now, thankfully, we can actually solve and cancel these x squareds out. It would be a more difficult problem if we could not do that. So I'm just going to get the 32x by itself. Oops, this guy doesn't really cancel. We subtract him. We get 320 equals 32x. This solves pretty nice like. X is equal to 10. That's it. So we'll do another one just so you can see that FOIL step again, try to visualize it, and then we'll move on. So in the figure, IK is tangent. That means we have a 90 degree here. To circle J, add K. Find the value of X. So once again, we have a leg, we have a leg. So that would be X squared plus 16 squared has to equal the hypotenuse, which is X plus 8 all squared. Okay, so we need to distribute. This 2 means you have to duplicate that whole thing. And you could even call this, instead of foiling, you can call it double distribution, where you distribute X to both terms in the other parenthesis, and you distribute 8 to both terms in the other one. Foiling works for a lot of people. That might not help you too much. Anyway, I'm going to combine some steps into one. I have X squared. My 2 middle terms will combine 8x plus 8x and give me 16x, and then plus 64. And then I solve just like the other one. So 16x is going to equal 192, I believe. Divide by 16, and x ends up equaling 12 when you plug that in. Okay? 10.11, if 2 segments from the same exterior point are tangent to a circle, then they are congruent. So a couple things you have to know. You have to know that they come to the same exterior point. You also must know that these are both tangent lines. If they're not, this doesn't work. But if you know those 2 things, you know that these segments are congruent. Okay? So it tells us segment AC and BC are tangent. So tangent, they both meet at the point C. So we can say these are congruent and solve. So 5 is going to equal X, and we're already done with that. If it asks for the segment length, we could go ahead and find it if we wanted. All right, next one, MN and MP are tangent. They come to the point M, which means we can set these congruent to each other or equal to solve. Make sure, catch your signs. We get 3x equals 21. 3 is equal to 7. Okay? Now we can use the same idea for problems of circumscribed shapes. So real quick, I want to point out that we had been talking about, actually let's do it this way. We had been talking about inscribed shapes, where the shape is inside the circle. Now we have circumscribed, which is a shape, doesn't even have to be a triangle, is around the circle. See, I did pretty okay. Sometimes it's hard to draw it so that way it matches up. Anyway, this just tells us that we have a bunch of tangents. Okay? So, it's easier to look at this. This is circumscribed. And because all of these lines are tangents, we can use what we just learned in the previous theorem, 10.11, to say, okay, these come to point S, which means this tangent line from S to N is congruent from S to M. And N to Q is congruent from Q to L. and L to R is congruent to R to M. Now we want to find the perimeter here, which means we're going to end up adding all the sides. We just need to find out what they all are. So if SM is 10, SN is 10. If QN is 2, then QL is also 2. And if LR is 8 minus 2, or 6, then MR is also 6. So you go ahead and add each of these up. Make sure don't double count the 8 or something like that. And we solve, and I believe we end up getting 36 centimeters. Make sure, check your unit as our perimeter. Okay? And we do it again. A bouncy ball is marked in a triangular marketed in a triangular package to pique the customer's interest. If this triangle is circumscribed about circle G, find the perimeter. So we do the same thing. We know these guys are congruent. We know these are congruent because they come to the same points and they are tangent. And same thing here. So we know AE is 12, CD is 6, DB must be 10 then, so BF is also 10. And let's see, we get 10 plus 10. We get, let's just come over here. We have a calculator to use, why not? We get 56. So 56 centimeters is our perimeter. All right, that's all I have. Have a great day.